Hello there, Mr. Watts here. For today's lesson, we're going to consider differentiation as part of the Year 13 Maths course. We're going to consider how to differentiate a variety of different functions, and we're going to link all of those together with this thing called the chain rule and how that can be applied to help us differentiate more complex versions of some standard functions. So as part of the Year 12 course, we've already considered how to differentiate functions of x with a power. There's a quick example here to jog your memory. We've got this method where we multiply by the power and then reduce the power by 1. We're going to use this rule for differentiation to help us differentiate functions looking something like this, where we've got a function of x inside a bracket raised to a power. So it's similar to what we've already got, but instead of x raised to a power, we have a function of x raised to a power instead. We'd call this thing a composite function. It's a function of a function. And this is where the chain rule comes in. We can use this to help us differentiate without having to go to the trouble of expanding the brackets. So this is what our chain rule looks like. You should be fairly happy that this makes sense. We've got dy by dx. We're going to calculate dy by dx by working out two separate derivatives. We're going to work out dy by du, and then we're going to multiply that by du by dx. And if you look at this, we've got a du on the bottom of the first derivative, we've got a d on the top of the second derivative. It doesn't technically work like this, but you can see that it looks like they will cancel out to leave us with dy dx. The u part is what we're going to use to represent the function inside the bracket, the thing that's made it more complicated than what we dealt with before. So this first derivative, dy by du, is going to be differentiating the bracket as a whole, where we'll multiply by the power of the bracket and reduce the power of the bracket by 1. This second derivative, I always think of it as a correction to deal with the fact we weren't just having x with a power, we had 3x plus 1 with a power, so we have to differentiate the 3x plus 1 and then we'd multiply by the derivative of the first thing. Let's try some examples to check how this is going to work. So if we consider the top example here, we've done a differentiate y equals 3x plus 1 to the power 4. You can work this out by writing down that u equals 3x plus 1 and then running everything through in terms of this. We'll do this for the first question, but we're then going to try and avoid having to use this method. It's quite long-winded. It makes it more complicated than we need to. So we're going to try and avoid using that. So we'd like to use our chain rule to work out dy by dx. So to work out dy by dx, we know that we want to use dy by du, and we're going to multiply by du by dx. And we've already decided that we're going to use u is 3x plus 1. If u is 3x plus 1, that means we've actually got that y equals u to the power 4. So if we differentiate these two separate things, if we differentiate y, we're going to get dy by du because we've got y equals u to the power 4. So multiply by the power and subtract 1 from the power. That's the dy by du dealt with. If we differentiate the u equation, we're going to come out with du by dx. Du by dx is just going to be 3. So if we put these two pieces together to work out our dy by dx, we're going to get 4 u to the 3 multiplied by 3. Now we don't really want our final answer here to have u's involved, so we're going to substitute back in what we know u equals, and if we also simplify, the 3 times 4 makes 12. So instead of u cubed, I'm going to write 3x plus 1 all cubed. So if we just take a look at that answer, do we think we could have got there without having to do all that extra working out? So if we start with the original function, y equals 3x plus 1 to the power 4. So what we've actually done is we've multiplied by the power 4 and we've reduced the power on the bracket to a power 3. And then we've had to not forget about this thing I always think of as a correction. if we differentiate 3x plus 1, that gives us 3. So the 4 from multiplying by the power and the 3 from differentiating inside the bracket is why we ended up with this 12 on the front. Okay, let's try this more advanced example, but we're actually going to set the working out without having to show the u's in there and see if we can cope with that. So we want to work out dy by dx. So if we treat it as a function as a whole, we're going to multiply by the power of the bracket, which is 3. Everything inside the brackets is going to remain the same. And we're going to reduce the power on the bracket by 1 to make that 2. So this term we've just worked out is our dy by du term. We are then going to multiply that by our du dx, which is what we get if we differentiate what is inside the brackets. So if I differentiate the inside of the brackets, I'm going to come out with 10x minus 2. Because this time, when we differentiate the inside of the brackets, we've got a linear function, we're going to have to treat that as having brackets involved to make sure when we multiply, that multiplication would happen correctly. If we tidy our final answer up, I would probably leave it in factorised form. So I'd go for something like 3, 10x minus 2, and then we'd have 5x squared minus 2x squared. Okay, so this shouldn't be too tough to deal with. We're using the rule we normally use of multiplying by the power and reducing the power by 1 on the bracket. And then as a correction, we have to multiply by what we get when we differentiate the inside of the brackets as well. Okay, we also need to apply the chain rule to some different functions. Before we can apply some different functions, we do need to think about what they may differentiate to give. So we are expected this year to consider differentiating the trig functions. Okay, we're just going to run through a brief example of how that can work. So we've got an idea now how to differentiate y equals sine x. If we differentiate y equals sine x, we'd get that dy by dx would equal cos x. We can make very similar considerations for the cosine curve. So we now have the result that if we have y equals cosine x, then if we differentiate that to get dy by dx, we're going to end up with y equals negative sine x. Because these results are quite similar, people often struggle to remember. So what I always use is this circle
This
here.
image shows the graph
So
of
we've
y
filled it out
equals
with
sin
s and
x.
c to stand for sine and
If you notice
cosine,
the scales,
and then
we are having
underneath
to
we've
measure
used
angles
negative
here in
s and
radians
negative
again,
sine x and
as
negative
mentioned
c
previously,
cosine x.
rather than degrees.
And if we follow this circle
more
round
detail at a
clockwise,
later date.
it allows us to
If we're
have a quick
considering
way
how
of
to
remembering how to
differentiate
the
the
my
sin x
students over the
curve,
last few years, I like to
we
call this the
could consider the
Snapchat
gradient
circle.
in different
So you
points.
fill it in with the s and the
So
c's,
we
and then
start
you
off
just
at
need to remember to go
0,
around
0.
clockwise.
At
And
0,
that
0,
will
the
tell you
gradient is
that
positive,
sine
and
differentiates
it
to
also has a
cosine,
maximum value.
cosine to negative sine, negative
We've
sine
put
to
it somewhere
negative
around here.
cosine, and then negative cosine would differentiate back around
If
to
we
sine.
consider
So it's a quick way of remembering those.
the maximum
rules.
value here, the gradient of the tangent at that point would have a value of 0. We move along to another significant value. We've got coordinates of pi 0. The gradient at this point has a negative value, and it would be the maximum negative value. The next point of interest is the minimum point, which would be at 3 pi over 2. And again, that's going to have a gradient of 0 because it's a stationary point. And then finally, if we consider the x value of 2 pi, this has a gradient which is a maximum positive value again, which we could plot something like that. So we have these 5 blue points that we could join up. We could join up with a straight line, but actually they're going to join up with a curve, and you may be able to spot a curve that you're familiar with, which will fit with those linked to trigonometry, which is actually the curve of y equals cosine x. So the cosine curve actually fits and matches with the gradient of the sine curve. So if the gradients match, that's how we can differentiate it. This time we've started off with the cosine curve, and we're going to do the same thing and consider key points on the curve and the value of the gradient at those points. So first of all, we're going to consider the point 0, 1. At that point, the gradient would be 0, so we'll plot that 0. If we then consider the x-intercept at pi over 2, that has a negative gradient, and it'd be a maximum negative gradient, so I'm going to plot that down here. If we then consider the minimum point with an x-coordinate of pi, that would again have a gradient back at 0. If we consider the curve where it's got an x-intercept again at 3 pi over 2, that has a positive maximum gradient, which I'm going to plot up here. And then finally, the final value, which is a maximum of x value of 2 pi, we're back to having a gradient of 0 again. So the green dots this time again fit with another trig curve. It's not quite one of our standard trig curves, it's a transformation of one of those. And the most common transformation of it we would consider is to use the negative sine curve. So the graph of y equals negative sine x would give us this mirrored version of your regular sine curve. We could also apply these to the chain rule. So using the ideas we talked about before, we're going to consider how the trig part would differentiate, and then we're going to do a correction for the fact that it's not sine x or cosine x, it's sine or cosine of some function of x. So if we consider this, we're trying to differentiate y equals negative cosine of 6x. So we're trying to work out dy by dx. Because we've got negative cosine is going to differentiate to positive sine. So we're going to end up with sine of 6x. Okay, the function on the end of trig is staying exactly the same. As a correction, because it's 6x and not just x, we need to make sure that we multiply by the 6. So if we differentiate 6x, that will give us a value of 6.
So simplifying our answer gives us 6 sine of 6x. And that would be our final answer to dy dx. In a slightly more advanced example, so we're trying to differentiate this time y equals -3 sine of 4x squared. So because we've got negative sign is going to differentiate negative cosine. You should notice that I've left the 3 well alone at the front for now, and we've left whatever's on the end of the trig function has stayed the same as well. And as our correction to deal with the chain rule, we need to multiply by what we get when we differentiate the 4x squared. So if we differentiate 4x squared, we are going to come out with 8x. So we can just tidy that up to give us a nice final result. So that's going to give us -24x cosine of 4x squared. Okay, we also need to consider this year how to differentiate e to the x and natural log of x. So differentiating e to the x, we've already looked at in year 12 and it's really easy to differentiate, it just stays the same. So if y equals e to the x, then dy by dx equals e to the x. That's a fact you should already know. The natural log function also differentiates nicely because it's linked to e. So if y equals natural log x, dy by dx actually just equals 1 over x. And we'll prove this to you a little bit later on in the class. Again, we're going to use the chain rule to apply this to functions that are linked to e to the x and natural log x using these two starting rules. So for the top problem up here, we've got y equals 3 e to the 5x. So to work out dy by dx, for e to the x, we don't actually have to do anything. We differentiate e to the x, it stays the same, so that is going to stay exactly the same. Using our chain rule, because it's not e to the x, it's e to the 5x, we need to differentiate 5x, which will give us a value of 5, so we end up having to multiply by 5. So that's given us a value of 15 e to the 5x. So note the 5x has stayed the same, because when you differentiate the exponential function it doesn't change, but we've had to multiply by 5 because it was 5x, not just x. If we try the slightly more advanced e to the x example, so to calculate dy by dx, if we differentiate the exponential function it stays the same, so all of this is going to stay the same to start with, and we're going to multiply by the derivative of the power. If I differentiate the power, which is 3x squared minus 1, I'm going to end up with 6x. So again, if we just tidy that final result up, we're going to end up with -12x e to the power of 3x squared minus 1. If we try the natural log examples, so if we try the basic example first, so natural log differentiates to 1 over. So because it's natural log of 6x, that will differentiate to 1 over 6x. To take our chain rule into account, we multiply by the derivative of the 6x, which is 6, which actually gives us a slightly unusual result, which gives us 6 over 6x, which just gives us 1 over x. Okay, this is actually an interesting result. If we actually differentiate natural log of any multiple of x, it would always simplify back down just to 1 over x. If we deal with a slightly more complicated example down here, so dy by dx, natural log of x differentiates to 1 over x. So we're going to start off by doing 1 over this function of x, but because of the chain rule, we need to multiply by the derivative of this function. So if we differentiate 2x squared minus 1, we end up with 4x. So to tidy that up, we would end up with 4x over 2x squared minus 1. Okay, the final type of function we're going to look at differentiating is a to the power x. So this could be any number raised to the power of x, not just e to the power x. And to be able to do this, we're going to consider using e to the power x to help, and thinking about our laws of indices and how we can link these two functions together. So all exponential curves could be transformed into a different exponential curve just by stretching it. So if we want to consider y equals a to the power x, this can be done by stretching e to the power x. So we're going to put a value of k in to allow us to have a scale factor for stretching the curve. So if we start off, we're considering that y equals a to the power x and y equals e to the power kx. We want both these curves to be exactly the same, so we're going to set them equal to each other. To try and figure out what k is, we're going to take natural logs of both sides. And using our laws of logs, we can move the powers to the front. And if you actually have a look at this statement, there's actually quite a bit that cancels down in here. We can cancel out by dividing through by x to remove the x's. And if you actually take the natural log of e, that turns out just to be 1. So this has actually given us a k value of natural log a. So if we put that back into what we were considering at the start, that means y equals x natural log a. We tend to write the x before the natural log just so we don't get confused about that it shouldn't be on the end of the log. So our k value is natural log a, so we've got e to the natural log a times by x. If we differentiate this using our chain rule and our rules for differentiating e to the x, we'd get natural log a, and then we'd get e to the x natural log a. The e to the x term has stayed the same, and we've multiplied by what we get if we differentiate that power. E to the x natural log a is actually y, and we had these two definitions of y in the first place. One was a to the x, the other was this e to the kx. So actually if we put the a to the x definition back in, we've got this definition for differentiating y equals a to the x that's got a's and x's in, looking like the form that we wanted. And this is another useful result that you're expected to know as a fact. You could potentially be asked to prove it and show where this comes from, but usually it's good enough just to know this as a factual result, then you can use that to answer questions. So if we try and find a couple of examples using this fact, so we're trying to differentiate y equals 2 to the power x. So this literally is just going to be using the fact that we've just talked about. So if we want to work out dy by dx, we're going to end up with doing natural log of 2, and that's going to have to be multiplied by 2 to the power x. And it's actually quite a tricky statement to write without the multiplication sign in. We could write it like this with a multiply symbol in. You could potentially write it as 2 to the power x and then put the natural log 2 on the end instead to possibly tidy it up. So there was no chain rule actually involved in this question apart from deriving the formula in the first place. If we try the one down here, this is also involving a bit of chain rule as well as this new rule. So differentiating as normal using our new rule, okay, it's going to stay as 3 to the power 5x, and we would need a natural log of 3 because our a value was 3. So that's our normal differentiation. But because it wasn't power x, it was power 5x. If I differentiate 5x, I get 5, so I've had to multiply it by 5 as well. So our tidied up version, I'm probably going to go for 3 to the power 5x. And I think we're going to have to put a multiply sign in to make this clear, multiplied by 5, ln 3. Okay, so using Our new rule for differentiation, we've kept the a to the power x the same. We needed natural log 3 because 3 was the base number. The multiply by 5 is coming from the chain rule, because if we differentiate the power 5x, we come out with a 5. So if we just consider everything we've looked at, I would really strongly recommend making some summary notes of these different rules for differentiation, so you've got them to hand, and until you're confident, you can keep looking back and double checking in there. You are expected to be confident with all the methods discussed and know these as facts from memory. And I'd like to think about really the similarities between using the chain rule and all these different functions. Again, the chain rule has worked in exactly the same way with all these functions, and I like to think about it as this: we multiply by a correction on the end, because it wasn't x to the power something, it was a function of x. It wasn't sine x, it was sine a function of x. We do what we would normally do to differentiate the main function, and then we times by this correction, which is the derivative of the thing that's made it a bit more complicated than normal. Okay, we will be extending this method and applying it to different types of problems in the future, so do make sure you are confident with the ideas discussed. Okay, thank you very much for taking the time to listen.